Hello everyone, it's time for class again. This is ECE317 digital signal processing. Welcome. Okay, ECE317. This is the second week Friday's class. Last time we have studied this different kind of Fourier transform, right? So we have Fourier transform. Three kind of Fourier transform. CTFT is a continuous time Fourier transform, and DTFT is discrete time Fourier transform, and then DFT, so just discrete Fourier transform. For CTFT, it works like this. You start from signal f of t. Then you will try to write it as like this. You want to write this equal to, I put it here. It is 1 over 2 pi. It's an integral of certain weight. Actually, this is Fourier transform. F of j omega times e to the j omega t d omega. This is the inverse CTFT. E to the j omega t is cosine of omega t plus j sine of omega t. So this is a mixture of cosine and sine. Both they have omega at the same frequency, omega, but one is in real part, cosine is in real part, and sine is in the imaginary part. Right. So we write f of t in terms of this. The integral means kind of a mixture, kind of summation, limit of summation. Right. Integral is a limit of summation. So it's a combination of these sinusoid with different omega. Omega run from negative infinity to positive infinity. And this capital F is a weight. Right. We call it a spectrum, but it's a weight. And how to get this weight? That is a CTFT. We have capital F of j omega, which is an integral from negative infinite to positive infinite, f of t times e to the negative j capital omega t dt. So this is a CTFT. And then DTFT. Similar. Now is a x of n. Right? It's a signal times n now. Right? Use x for the name of signal. And we want this is also an integral, similar with continuous times case. But now the frequency just run from negative pi to positive pi. One cycle. You can also choose like 0 to 2 pi. Right? Integral from 0 to 2 pi. The result is the same. And here will be some capital X as a weight. And inside the capital X, we use the notation e to the j omega. But actually here the value changed. The variable is omega. Right? It's a function of omega. Then times e to the j lowercase omega n d omega. Both capital omega and lowercase omega here, they are frequency, but I use capital and lowercase to separate two cases. When you look at capital omega, you know it's for continuous time signal. When you look at lowercase omega, that means the signal is discrete time signal. Alright. Okay, so this is called DTFT inverse of DTFT. And similar with that, right? E to the j omega n now is cosine of omega n plus j sine of omega n. Right? It's a sinusoid. So this you write this x, the signal x, as a mixture of some sinusoid. and each component, each sinusoid, you have a weight. So what is this weight? The weight can be obtained by DTFT, which is a capital X of e to the j omega equal to, now is a summation of x of n times e to the negative j omega n, and run from negative to positive infinity. Alright, so this is a CTFT, DTFT already, right? Okay. Then we have the third one, DFT. Why do we need a DFT? Because we need to calculate it in the computer. We still have x of n, but this time n will run from 0 to some n minus 1. I put equal here, n minus 1. So totally n numbers. And this one, for DTFT, the n is run from negative to positive infinite. Right, you have infinite terms. Now DFT we only have finite terms. And this one we'll write as, okay, I write again. Xn, we want to represent it as, now it's not integral, it's a summation. Summation 1 over n. Okay, we need an n here. 1 over n, not 1 over 2 pi, 1 over n. Then here's some capital X, or summation, sorry. Integral now replaced by summation. Summation of some capital X of k. And here's a still sinusoid, the e to the j, okay, frequency times n. But what is the frequency? Okay, there will be 2 pi over n times k. Right, this k. This is also k. Yeah. Okay, this is the value related with omega, right? But now we only have finite numbers, and then times n. We still need n, right? So omega n. Here's a omega n, omega t. Here's a omega n. Here's also omega n, but omega is this one, 2 pi over n times k. So why is it 2 pi over n? Actually, the thing is like this: from 0 to 2 pi, and separated by n pieces, right? So each one is, this is a 2 pi over n times 1. Second, this is a 2 pi over n times 2. This is a 2 pi over n times 3, and so on. And this one is just 2 pi over n times 0, right? It is 0. So we choose this point, this point, this point, this point, until this point. So this is a k. K run from 0 to n minus 1. Right? 0, 1, 2 until this is a 2 pi over n times n minus 1. So they are the frequency. Right? Frequency. Okay. Then let me see. We have this one, right? Okay, we need to determine what is this capital X. What is this capital X? Okay, how to get it? This is a DFT, discrete Fourier transform. We have capital X of k equal to summation k run from 0, not k is here. This is n. N, use this n. N run from 0 to n minus 1. Actually similar with these, but the index run from 0 to n minus 1. Right? N run from 0 to n minus 1. N x of n times e to the negative j. Okay, omega, I still use this omega. This is a 2 pi over n k times n. Alright. So this is a DFT, and this formula is inverse of DFT. Okay, so last time we introduced these three. Now we consider one more thing. How do they related? Right? These three, these should be related, right? How do they relate? Yeah, right. Okay, we can use the example to explain it. We consider a signal f of t is like just e to the negative t u of t. E to the negative t looks like this, and the unit step u of t times u of t on it, so the result function looks like this. Here's 1, right? This is t. This is f of t. Then by CTFT we can have capital not x, f, capital F of j omega. We can have this one. Actually this is 1 plus j capital omega. It is just 1 over j capital omega. Am I good? Search online, you can have the Fourier transform tables of Fourier transform. Any tables you can find this. And then f of t, right? F of t. We take sample on it. Then we can have a discrete time signal. We can have discrete time signal. So I use x of n, which is e to the negative. Now t is a capital T times n. Then here is u of n. It looks like this. This is n. This is n, right? This is this one. We write it this one. So t is a. We take sample. Step t. So every capital T you take one sample. This is t. Right? This is n. Here is just 0, n is 0 or 1, 2, 3, and so on, right? But how do you get this value? You take samples from the continuous time signal. Every t as a step, as an interval. Then you take next value, right? Every t you take one value. Then you have this one. This is a discrete time signal. And we can write this as e to the negative t times n, power of n, then u of n. This one, you can have DTFT. Actually, this one you still use table. From table you can find this kind of signal. We already have the DTFT. This is a capital X of e to the j omega equal to, yeah, the notation now it looks somehow not so convenient, but when you use to it, you think it's fine. And later we will see we use this kind of way to denote this function. We have some benefit. All right. Okay. So this is 1 over 1. There will be 1 minus. Okay. This is I write this as a. This I consider this a. This will be e to the negative t. Then e to the j omega, negative j omega. Okay, so we have this one. We have this one. Yeah, this one is also by tables. And then, okay, here n is run from negative to positive infinite. Right, this is the case. Now we consider x of n for n run from 0 to some n minus 1 in this case. Then we can have capital X k. Okay, we can just use we have 3 different ways to calculate it, right? The most convenient way now we have MATLAB, we can just use FFT of x of n. Alright, we have this function, and this. Here's a list of value k run from 0 to n minus 1 related with frequency 2 pi over n times k, right? For every k, you have this value. this value will be the weight of the frequency components, the frequency this one, right? Okay, we have these three. Then how do they look like? So these three graphs will look like this. The f of j omega, actually this is a complex values, right? All these are complex values, so I check the magnitude of it in terms of omega. So it will looks like this. Will looks like this. Here's the function. When omega is 0, when capital omega is 0, it is 1. When omega increase, the value will turn to be lower and lower, right? Things like this. So here's 1. And the other one, the second capital X looks like this. So it is a lowercase omega. It all looks like this. Looks like this. It is use 2 pi as a period. 2 pi as a period. This one is x of e to the j omega. Use 2 pi as a period. And the third one x of k. Third one x of k. It will be, this is n. So it will be some point here. Totally, this is 0, and the last point, this one is n minus 1. N equal to lowercase n equal to n minus 1. So we have some point, discrete values, right? Discrete values. We have this one. And the relation between these three is, for the first two, if you check here, here's a pi, here's a negative pi. So it should be in the middle, right? Middle, okay. So these two part, they are kind of approximate. Not exactly same, but very close. Very close. These two, you can think they are same. They are same. And here, these dots, they are just along the curve. So from here is a kind of sampling. So okay, this part is approximate. And this part kind of symbols, right? You take symbol, you pick some point, you get this one, and you get this one. So this part are symbols of this curve. So when do you calculate? You use FFT in the computer. You can apply the function FFT, right? You use this one, you will get this part. So if you want to know what is the Fourier transform of this continuous time signal, you want to know this one. What is this? By computer, you can only get this one. So this one, you move this part to that side, then you get a dot here, right? Some dots, some symbols here, and these two are approximate, so you get that one. So we have another function. The name is FFT shift FFT or FFT shift. Then you will have, you keep this part, and move this part to the other side. So you will have a result looks like this. This part according to here. Right. This part, it is this part according to this part, and then you can repeat it periodically. You can have the whole signal of these. All right. So now we know the relation between these three. Of course, you also need what is value here. You you will have lab experiment related with this kind of things. All right, good. All right. Now we try to consider systems. So far we are studying signals, right? Now we start consider systems.
So what is a system? You should already know that, right? Things like you have a machine, you have a circuit, or you have whatever. Then you give an input signal. This is system. And this side you can have output. If you give the input, the system will give you a response. You give the output, so this is a system, right? This system. For example, you have a light in your home, right? Every room you have a light, and you have a switch. You can say this is a system. You give input on the switch. The switch is the side you give input. Then the output is the light. You turn it on. You give some push. Okay, the light is to, like, you think the level of the light go to 100%. And you push the input side again. The output side is will give you the light level to 0, no light, turn off, right? Things like that. You can also consider you have a cell phone. Your cell phone is also a system, right? When you call it, then the system will give an output that is a real wave, right? You call it, you will give a wave, the wave to some antenna, and go finally to another cell phone. And when someone calls you, similar thing. They have a signal go into your phone, and the phone give output is a voice. Then you can hear, oh, someone calling you, right? So this is we have a lot of things. You go around, you check around all your daily life, you can find a lot of systems. Okay, then we consider, in this course, we really consider the system with both sides, they are signal in discrete time case. You can also have input is a continuous time signal and output is a continuous time signal, right? We call that is that kind of systems analog signal, analog system. But here we just consider this case. Input side, output side, they are discrete time signals. So this is a discrete time signal. And usually you can give a name of this system. Like for example, you just use S for system, S of a system. Then you can also write Y of n is this system with input, X of n as input. Yeah, notation. This notation is similar with a function, right? You use X as input, you have output Y. Like you give a value of the variable, then you can have a value of this function, right? Similar like that. But now this is not the input side is a sequence of value, and output side is also a sequence of value. Right? You can say this is generalization of a function. Generalization of a function. Right? And then for the system, we have a problem. So what kind of system do we have? The different system, we have several kind of things. We can say this is classification of systems. Classification of systems. The first one we call it memoryless. Memoryless system. Memoryless system. This is the case we do not need a memory. Memoryless system. The thing like Y of n. Yeah, I use example to explain. So Y of n equal to like 3 times x squared of n. So this is memoryless. When x, you know the value of x at time n, then you can have the output of y at time n. So here we can, if this is n, this is for n, if this is n, the current time, then here's n plus 1. This will be future time, right? Future time. And minus 1 is past time, right? Past time. Right? The old time, the previous time, the previous time. Right. So this y of n only depends on current time, current input. Right. Output only depend on current input. Current input. This is a memoryless. And another example. You see y of n equal to, for example, 1/3. Here's a x of n plus 1 plus x of n plus x of n minus 1. This is not memoryless. Right, because you have some old date, you have some future date. Right? This is current date. You need the input side, you need current input, some old input. Also, you even need some future input. So we call this is a memoryless system. You need to remember. You need to remember something. Right? At time n, you want to find the output. You need these values. You also need some old values. Those old values you need to save it in memory. And you also need a future date. You need to save the future date in a memory. Here. Okay, it sounds good. Sounds weird, right? Okay, we have a second type of system. It's causal system. Causal system. What is causal system? Causal system, that means the output output do not depend, does not depend on future input. Yeah, some like this example. I say this is a example 1, example 2, then example 2 is not a causal system. It's not a causal system. Because depending on future, this is a future value, right? Some future value. Like suppose now is I know, like now is like 3 o'clock. You think now is 3 o'clock, then 4 o'clock will be future, right? 5 o'clock is also even far future. So if a system, the output depending on future input, we call it a non-causal system. Non-causal system. Non-causal system. Non-causal system. It's not a causal system. Or uncausal system. The uncausal system. Or something. Anyway, yeah, it's a causal system. This is not causal system. This is not causal system. And we can have another example for causal. I have output y of n equal to x of n minus x of n minus 1. Okay, this is a causal, right? This is a causal. This is a causal. Alright. And actually here we have some name for this example. This is a moving average. Moving average system. You take 3 values, take the average. And we can more generally, you can consider 4 elements and divide by 4. That is also moving average. You can consider like 10, even 10, or even more any. You do summation of some nearby signal, nearby values of input, right? This is 1 by 1. This is n plus 1. This is n. This is n minus 1, right? Nearby. You do summation of them and take average. We call that is a moving average system. So at every time n, you consider nearby values, do average as the output. And for different n, you use different values for average. You larger n, then you need other values of x, take the average. So when the time is moving around, moving forward, you always consider some values nearby that time n. They take average as the output. So we call this is a moving average system. And this is a difference system. This is a difference system. Yes. Difference system. They give the difference between nearby 2 values. Right? 2 values. You check 2 values of the input signal. You take 2 values, nearby values. You check the difference between them as the output. So this is a difference system. Difference system. Right? So this is not causal. This is causal. This is causal. Example 3. This is causal. Right? This is causal. Yeah. Example 2 is not causal. The first one actually is also causal, right? Yeah. Just depending on current state. The current input is also causal. Okay. This is a. We have memoryless system. We have causal system. And we also have, let me see, we have time invariant system. Right? This is when time is changing, the sense might be also changing. Time invariant system. 1, 2, 3. Time invariant system. This system you can consider it will not change according to time. Things like today you use your phone, you give certain kind of input, then the system gives you a response. The next day you do the same thing, the system will give you same response. Right? So the system is time invariant. Yeah. Then if it is changing, so different day you give same input, but the response, the output is different, then that is not time invariant. That is a time variant. So the things like we can describe these by a formula like this. We suppose the system is S. This is system, right? System's name. And input. This is input X. Right? Now I shift this n minus nd. I use a shifted x as the input. Then this one will equal to the output x of n shift to nd. Oh, I do write this way. If x of n gave output y of n, then x of n gave output y n minus dn, and ddn. Then x of n minus nd gives output y of n minus nd. And this is it. Yeah, things like that. So if input x, you can have y. Then you use a different time, you still have y. You use this x, then you still have y. Just the time that is happening different time. Like for example, you have x of n. Suppose this is x of n. Then you have y of n. So this is y of n, and shift. This is nd. Shift. You give shift. This is y of n minus nd. You shift x by nd. Then here's the system, right? Here's the system S. Here's the system S. You will have same thing of y, but shifted to nd. Shifted by nd. This is nd here. ND here. So you give same waveform. You should look at the waveform of input. They are same, right? Just happen in different time. This will happen at time equal to 0, and this will happen at time equal to ND. And then the output side, they will have the same waveform, but the start time is different. This signal will start from n equal to 0, and this signal start from n equal to nd, right? Alright. So this is time invariant system. And we can look at the previous examples. Actually, all of these, they are time invariant. Why? You look at the first one. The output, you look at the formula, you have input value times 3. So no matter what is the time you gave the input, the output is just 3 times the square of it, right? So this is time invariant. And this one is also similar. You have 3 values of input and do summation and divide by 3. So this operation, right, to summation and divide by 3, it won't change no matter what is the n. So you shift n or do not shift n, doesn't matter. The output always looks like this. So this is also time invariant. And similar, this is also time invariant. So what case is a time invariant? I give you an example for time invariant. Okay, examples. 1, 2, 3. All of them, they are time invariant. And example 4. Y of n equal to like n minus 2 times x of n. This one is time variant. When time is different, this coefficient is changing. That is depending on n. So like when n increasing, this coefficient will tend to be larger, right? If n is 100, this is 98. If n is 1000, it will be 900 and something, right? So this coefficient is changing according to time. The coefficient changing according to time. You give input. If you give input in different time, this coefficient will change. So the output waveform will be different. Right? The same like if this is the input, this is xn, the yn will be n minus 2 times x. So this n is 0, right? So times -2. This is yn, right? Then when n is large, when turned it to here, like shifted by 4, shifted by 4 as input, then the output side is what? It is this time is 4, right? 4 minus 2 times the value is 1. Now here is 1. here will be -2. Now it's 4, then 4 minus 2 is 2, 2 times it. So at time 4, you have this as output. So this is y of n for xn minus 4. This is x of n minus 4. Right? It changes. If in no shift, you times -2 on it. You shift by 4, you times +2 on it. Now it's +2, right? +2. So different time you have different output. The value of output is different, right? Yeah, you can always check the time invariant by this kind of thing. You just use the impulse as input. This is unit impulse, right? You check what is output, and you shift. You check what is output. If these two they have same waveform, then it is time invariant. Otherwise, it is time variant. Time variant. This is time variant. Yeah, this is time variant because this coefficient is changing. You have coefficient changing. You have something other than x is changing on time. Right? Like this one, other than x, nothing changes according to time. Right? Yeah. This one also, other than x, nothing changes on time. Yeah. Okay, so this is I have 1, 2, 3 times. In total, you have 5 different things. Okay, the fourth type of system. This is linear system. Linear system. So what is a linear system? Things like that. It has 2 features. Suppose this is a system with input x of n as input. Now I times a constant a in front of the input signal. This will equal to a times s of x of n. This is one feature. You times n times the constant in input side, they will be same as times this same a in output side. And also another feature, x1 of n plus x2 of n. Suppose we have 2 signals as input. We do a summation firstly, then put them into the system. This gives you output, right? This output will equal to you just use the first one as input plus just use the second one as input. So that means when you have 2 signals, you want to do a summation and put them in a system. You have 2 ways to do it. You do summation firstly, then put it in the system, or you use these 2 signals as input separately. Then you get 2 output, right? You do summation on that 2 output, you can also get the same result. So if a system satisfies these 2, it is linear. It is linear. Alright, we can go back to see about our examples. Example 1. Example 1. That is y of n equal to 3x squared of n. Okay, then we can see as of like a times x of n will give us 3 of a x of n with square, that is 3a squared of x squared of n, right? This is a output related with input. Square of input times 3. Square of input times 3. That is output. Now we use a times x as input. So you need a square of input times 3 as output. And this is a 3 times a squared times x squared. Okay. And a, if you put a in the front, is a is still a, and this is a 3 times input. So totally is this one. it is xn times 3a in front, and this is x squared. This is xn squared times 3a squared in front. Are they same? They are different only if a is 1, right? For other a, they are different. Here should be for any a. For any a, right? So they are not same. For any, only if 0 they are same, right? For any. So we say this is not a linear system. Right, this is not a linear system. And okay, example 2. Y of n equal to 1/3 x of n plus 1, the moving average one, right? X of n and x of n minus 1. Is this linear? Okay, you need to check 2. You need to check 2. Check first, check second. If first satisfied, then you need to check second. If like similar with example 1, the first condition does not hold, then you say it's not a linear system, right? For this one, you can see S of a times input, a times x as the input, then it will be 1/3 of the input value is ax at n plus 1 and ax at time n and ax at time n minus 1. Oh, this is just you move a in front, right? A times 1/3 of x of n plus 1, right? You move a in front. You move a in front. All these three terms has a as a factor, right? So I move it in front. All right. Another one, yeah, like this, right? Okay, so this is a times s of x of n, right? This part is just s of x of n. So we have the first condition hold. We have the first condition. Now we check the second condition. Check the second condition. Second condition, S of, now we consider, suppose you have two signals as input. Then output side will be 1/3 of the input in the time n plus 1, the input at time n plus 1, right? Input is summation of x1 and x2 at time n plus 1. And the input at time n and the input at time n minus 1 . Alright, what it is? Of course, this is obviously this equal to the output. Just use x1 as input plus the output of the system when only x2 as input, right? You consider the first three, that is the first S. The second three of them, this is second S, right? Summation divided by 3, summation divided by 3. So it is this one. Alright, by these two, so the system is a linear system. This is a linear. This is linear. And let me see, we have example 3. Actually, example 3 is also linear. You can prove it very similar with the second one. And example 4. Do I have example 4? I think I have example 4. Where I put it? Example 4 is here. Yeah, example 4. example 4, y of n equal to n minus 2 times x of n. So whether it is linear or not, similar thing. We check that two features of a linear system. That two features are here. Okay. So the first feature, s of a times input, you use this as input, then output will be n minus 2 times the input. Okay, so you can move a in the front, you have n minus 2 times x of n. Okay, it works, right? This is a times s of x of n. Okay, and the second, we want to check this one, x1 plus x2. We have two signals as input, right? We do summation as input. What will happen? The output will be n minus 2 times the input. Okay, it still works, right? So this is equal to n minus 2 times x1 of n and n minus 2 times x2 of n. So which is s of x1 and s of x2 also work. So we know this is linear. This is linear. Alright. Yeah. And I can give one more example which is not linear. Example 5. We have y of n equal to 3x n plus 1 plus 4. Okay. So this is also system, right? Then we can see if we times a on x, we use this as input. What will be output? The output is 3 of the input at time n plus 1 and plus 4, right? Yeah. So output is 3 of input at time n plus 1, then plus 4. So 3 of input at time n plus 1 plus 4. Then we want this equal to s of x of n times 8, right? We want these two equal. We want these two equal. Are they same? This equal to a times, okay, s of x n is 3x at n plus 1 plus 4. Oh, this is 3ax of n plus 1 plus 4a. Oh, are they same? They are not same. You see? This is 4, this is 4a. This is 4a. Not same. Not same, different. Different. So s of a times x of n do not equal to a times s of x of n. So not linear. System is not linear. Not linear. Okay? Yeah. Actually, we have an easy way to check it. If you do more times, you can know that. That is, you look at the formula of the system. Formula of the system. When you have input side, there are only first order system. First order part. This is x. It means x to the power 1. Okay, this term is good. And we know this is a linear. Right? We just check which one? This one. We know it's linear because x, only x to 1. Right? X to the power to 1. And this is not. You have a 4. This 4 equal to 4 times x to the power 0. Right? xn to the power 0. It is not power to 1. So this is not linear. You check, you have a constant. That means you have term with 0 order. Linear must be first order. And we have another example with square, I think. Yeah, this one. Yeah. You have 3x squared. So you have a square here. Square on x. So this is not linear. And our result is also checked. This is not linear, right? X squared. Did I check? I think I do it somewhere. Sorry, I put it somewhere. Yeah. So you look at that, you know it is linear if all of the terms with x is just first order, then it's linear. It's linear. All right. We can have one more example. I just write it here. This is example 1, 2, 3, 4. Right? This is example 4. I just gave example 5. Now example 6. 6. Y of n, which is sine of n times like just x of n plus 3 of e to the 2n and x of n minus 1. This one, it is linear. It is linear. It is linear. Because you check x, the power of x is just 1. So this is linear. But not time invariant. Let's see, x has power 1. And this coefficient coefficient not will change according to n. Coefficients will change according to n, right? You see, this is coefficient. This is coefficient. We have n. When n is changing, the coefficient is changing. Then this is time, not time invariant. It's time variant. Time variant. This looks like when time changes, the feature of the system is changing. The coefficient is changing. Yeah. Okay. That's all for today. See you next time.